In this video, we are going to look at elastic potential energy. This is the last video in the series of videos on deformation of solids. In the first video, we looked at Hooke's law. Second video, we looked at stress, strain, and Young modulus. And now we are looking at energy considerations. Work is done when a spring is stretched by a force. The work done is stored as elastic potential energy or strain energy in the material. Strain energy is the ability of an object to do work as a result of the change of shape of the object. Molecules in the material gain molecular potential energy due to their displacement from their mean positions by the force. Provided the elastic limit has not been exceeded, the energy stored can be recovered. Now, we learned that F is equal to KE from Hooke's law. And then we also learned that if we plot a graph of F versus E, we are going to get a straight line graph that passes through the origin. So the area that is under the graph is equal to the energy that's going to be stored in the stretching process. So this area is a triangle, which is half base times height, which is half of F times E. Now, since we know that F is equal to KE, we can then say half KE squared, because KE then squared. I think we covered this again in the work, energy, and power section. So if you can go back to my video on work, energy, and power, you'll be able to get further clarification if you do not understand. Next, we want to talk about energy stored per unit volume. When the elastic limit is not exceeded, the energy stored, remember we said, is half F times E, and the volume of the material, e.g. of the wire, is AL. Now we want to find the energy stored per unit volume, so it's going to be that energy half Fe divided by the volume. Now if you analyze that closely, you find that this is half, and then this F over A is stress, and E over L is epsilon, which is strain. So half stress times strain is equal to the energy stored per unit volume. So the area under a stress-strain graph gives the energy stored per unit volume. The area is a measure of the toughness of the material. The larger the area, the more energy needed per unit volume to break the material. Now, just to elaborate further, on the F versus E graph, we said that the energy that we get there, or the area under the graph, is the energy stored. But then stress versus strain, energy stored per unit volumes. Please do not confuse the two. I think this marks the end of the topic. But before we do so, we need to do some examples, some further examples, just to illustrate. So the first example, that's example 4 in the deformation of solid series. A light spring of unextended length 14.2 centimeters is suspended vertically from a fixed point as illustrated in figure 4.1. A mass of weight 3.8 newtons is hung from the end of the spring as shown in figure 4.2. The length of the spring is now 16.3 centimeters. An additional force F that extends the spring does so that its length becomes 17.8 centimeters as shown in figure 4.3. The spring obeys Hooke's law and the elastic limit is not exceeded. Part 1 says, show that the spring constant of the spring is 1.8 newtons per centimeter. Now we know that K is equal to F over E, that's the spring constant, F over E. The force is 3.8 newtons. And then the extension is the new length, which is 16.3 minus the original length, 14.2, which then gives us that which is shown. So 3.8 over that gives you 1.8 newtons per centimeter. Now to convert that into newtons per meter, you've got to multiply by 100, which gives you 1.8 times 10 to the power 2 newtons per meter. Part 2 says for the extension of the spring from a length of 16.3 centimeters to a length of 17.8 centimeters. 1. Calculate the change in the gravitational potential energy of the mass on the spring. Now, gravitational potential energy or change in the gravitational potential energy is equal to mg delta h. So our delta h in this case is going to be 17.8 minus 16.3. Then we convert that into meters times 10 to the power of minus 2. So mg is our weight, which is 3.8. So 3.8 times that should give you the change in the gravitational potential energy, and that comes to be 0.057 joules. Secondly, show that the change in the elastic potential energy of the spring is 0.077 joules. Now the change in the elastic potential energy is equal to half ke2 squared minus half ke1 squared. Now E1 is the 16.3 minus 14.2. E2 is 17.8 minus 14.2, the extensions. So we remember we said half ke squared is our elastic potential energy. So the change in the elastic potential energy is going to be half of k times the extension. That's 17.8 minus 14.2, I suppose, and then that gives you the extension there. And then we say that squared minus k half ke1 squared. So if you do that well, you find that is 0.036 squared minus 0.021 squared times half k. And then this should give you 0.07695 joules, approximately 0.7077 joules. Lastly, the question requires you to determine the work done by the force. So work done by the force is equal to the change in the two energies. Remember, work is always done when energy is transferred from one form to another. So we're saying that change in the potential energy minus the elastic change in the elastic potential energy. So 0.077 minus 0.057, that should give you 0.020 joules. The last question on the topic, number 5. A vertical steel wire of length 0.80 meters and radius 1.0 millimeters is gradually loaded with a mass of 20 kgs applied to its lower end. Assuming that the proportional limit is not exceeded, calculate the extension. So we use the formula extension is equal to FL over EA. And then that should give you, I think you remember this formula where we were finding Young modulus. We said Young modulus, the big E is equal to FL over EA, small e on the denominator. So we can make small e the subject and it gives us that. So we then input the figures. F is 20, and then yes, 20 times G, which is 10, right? And then times the original length. The original length is 0.80 meters. Divided by Young modulus, we are given Young modulus is 2 times 10 to the power 11. And then the area will be pi r squared. Okay. So when you do that well, you find that you get 0.255 times 10 to the power of minus 3. Okay. So here we're saying that pi r squared, that's the, let's just go over the area again. Pi r squared, which is going to be, this is 10 to the minus 3 squared, will be 10 to the minus 6. That's why I have a 10 to the minus 6 there. Then energy stored, part C. Sorry, part B. The energy stored in the wire is half Fe, which is half times the force times the extension, which you've calculated in A. Then that should give you 25.5 times 10 to the power of minus 3 joules. which will be 2.55 times 10 to the power of minus 4 joules. Part C says the loss in the gravitational potential energy of the mass during loading account for the difference between B and C. So the loss is in P is equal to mgh, which is that. Then that gives you 51 times 10 to the power of minus 3. So the energy stored is half the loss in the gravitational potential energy. The energy stored is the molecular energy gained by the wire. The remainder is the energy dissipated as heat in the wire as the weight loses its kinetic energy after falling and comes to rest. If the load is suddenly applied, the extension will be twice the equilibrium extension obtained above. I think this marks the end of the topic on deformation of solids. Please let me know in the comments section how you're faring in this topic. If you're finding any part difficult, do not hesitate to ask. Signing out.